Bismillahirrahmanirrahim. Assalamu alaikum. Today we will cover 11th week lecture number 21 and 22. In the last lecture, we have covered free convection and forced convection and its numericals. Today we will cover numerical which have both utilization like conduction and convection. We also learned in the previous lecture the free convection, the application of free convection, like in this mosque we have natural convection flow by which the air is coming towards the bottom side of the space, and the hot air goes above uh, due to the heating between due to the heat taken place from a person, and the air uh, strike with the person, gets heated, becomes lighter and goes towards top side, and it leaving from the mosque or any building, and the the vacant space of this hot air taken place by the cold air, and by which we have a free natural convection flow. Also we have an example of a hot radiator, like radiator is placed in the bottom due to that when the cooling air, when the cold air strike with that, it goes above, the hot air goes above, and we have a uniform temperature of a room. But oppositely, if we need to place the air condition, we have to put that on the top side, because the air condition cool down the air, and the cold air comes towards bottom sides, and when the cold air strike with the human persons, becomes hotter again and goes on the top side. So we have a natural convection flow, and in this way the whole room temperature becomes uniform. Similarly, the example of fridge, the cooling plate capped on the top side, because the cold air strike with the cooling plate, so it goes toward down, and anything which is strike by the cold air becomes hotter and goes above, and the cycles goes on again and again. Anyway, today we have to cover this numerical that contains both conduction and convection. First, read out the numerical. Example 1.95. A solid plate with a thickness of 15 centimeter, a thermal conductivity of 80 watt per meter Kelvin, is being cooled at the upper surface by the air. The air temperature is 10 degree, while the temperature of the upper and lower surface of the surface plate are 50 and 60 respectively. Determine the convection heat transfer coefficient at the upper surface, and discuss whether the value is reasonable or not, whether the value is reasonable for forced convection of air or not. So actually what is being done in this numerical, that we have to determine the air is flowing from that solid plate is either free convection or forced convection. How can we determine this value? By getting the value of convection heat transfer coefficient. If the convection heat transfer coefficient value, we already learned that coefficient values of free and forced convection. So this is the table 1.5 tell us the free convection and forced convection values. If the H value is between 2 to 25, and the air is also a gas, so we can call them as a free convection. But if the value is more than 25, we can call them as a forced convection, like 25 to 250. So now we have to find out, we have to solve this numerical. Let's see what would be. Now here first clean. Okay, first we need to write down the data. The data is simple. We have x thickness is 15 centimeter. We have a k value is 80 unit. We have a temperature of T infinity is 10, and we have a temperature T1 of a plate is 60, and T2 is 50. Now we have to solve um, what is being doing is that the plate is the first heat is transfer from the solid plate from 60 to 50 degrees centigrade, and then from the upper side of the plate the heat is transferred through convection. So basically the conduction the heat transfer of conduction, q conduction will be equal to q convection for the steady flow if the parameter is not changing with the time. So we open the formula of conduction, that is Ka delta T over delta X, that is thickness, and Ha delta T. But both delta T have a different value. Like in a solid plate we have a T2 is 60, T1 is 60, T2 is 50, 60 minus 50, and we have this value 50 minus 10. This is T surface minus T infinity. So in both formulas we found out that the area of the plate is same. The surface area, this is basically side view. If we draw this is side value, this is the basically plate. The conduction is transferred from this point to this point. So in both cases the surface area is the same in the conduction and the convection. So this area, length and width of the solid plate is same as below. Okay, so the area is same for the conduction and convection, so we can cancel out like this. We don't need the area, value of area. So okay, now the value of K is 80 and T2 is 60 minus 50, and the thickness we have at I think we have a 15 centimeter, sorry, 15 centimeter. This is good. So 15 divided by 100, because we need to the value in the meter. So here we have to find out H, and the value of this is 50 minus I think 10 degree. The surrounding temperature is 10. Okay, now the H values over here. H is here. 50 minus 10 is 40. It goes on the bottom side. Okay, so by solving this we get the value of H is equal to 133 watt per meter Kelvin. Okay, watt per meter square, sorry, this is area. I can just we get the value of H is equal to 133 watt per meter square Kelvin. Okay, so value is more than 25, so we can call it as a forced convection, not a free convection. Got it? You can again cross check the values of forced convection of the gases between 25 to 250. So we have a value of 133, so it's a forced convection. Now come towards the radiation. Let's start the new topic of radiation. We have three modes: conduction, convection, and last one is the radiation. Radiation is the energy emitted by the matter in the form of electromagnetic waves or photons as a result photons as a result of the chances in the electronic configuration of atoms or molecules. The heat transfer studies we interested in thermal radiation, which is form of radiation emitted by the bodies because of their temperature. Unlike the conduction convection, the transfer of energy of the energy by the radiation doesn't require any presence of intervening medium. Like we are getting heat from the sun, and outside the earth there is a vacant space, there's a vacuum, so there's no medium. So still we are getting radiation, and we are getting heat transfer from the sun. For example, energy of the sun reaches the earth by radiation, and we have this table. These are the wavelength values of different radiations like electric power waves, radio waves, microwaves. Microwaves also nowadays used to heat up the cooking food items. And we are interested in this thermal radiation. In this thermal radiation we have two kinds of further radiation. That is a visible radiation, like you all see the radiation of the sun by yourself, by your naked eyes. And there is also some radiation called infrared radiation, but the infrared radiation is invisible. We cannot see the infrared radiation by our through our naked eye. We need some cameras by which we can see the thermal infrared radiation. But some animals also can see that infrared radiation. They have capability of it. Anyway, but nowadays we have special thermographic cameras. I used to give services to the industry in which I just have a thermal radiation camera. I just go there and check out the thermal radiation of their electrical equipments, their boilers, their HVAC equipment, and find out there the insulation gaps and heat loss from the boiler, etc. So it's another topic, but right now we have some special cameras available in the market. Especially you right now in the COVID time, you find out a laser gun by which you are getting the temperature of the human person. So basically the temperature can have a infrared radiation, thermal radiation sensor, which pyrometer, which calculate the temperature of person through radiation, because the laser gun which is pointing by the person is not touched to your body. So in between there's a gap, and the laser gun doesn't detect the temperature of the human person by convection or conduction. It detects the temperature through radiation. Okay, I hope you well understand. We have a different application, like for an example, if we place a hot object in some of a vacuum chamber and there is no any air or any medium, still we are getting heat from outside area. Like example of radiation, in winter we used to light up the stove and get the heat, and we get the thermal comfort. As in the winter, we due to the low temperature, we found very uncomfortable, and by lighting up the stove we get a very comfortable uh, we get very comfortable temperature and surrounding us. So these are the example. All the bodies at a temperature above absolute zero, that is minus 270, absolute zero Kelvin is minus 273 degrees centigrade. So any body which have a higher temperature than that, they radiate thermal radiations, like example of plants, furniture, people, etc. So as we learn the equation of convection, now we have a heat transfer rate equation for the radiation as well. That is Q radiation is equal to emissivity. We already learned emissivity in the starting of our course and their uses. The Stephen-Boltzmann constant, this is Stephen-Boltzmann constant. This is a constant value. It will not change by any factor. Emissivity value change with respect to the surface condition, like for the shiny emitter and absorber, we have a different values. Okay, lower the value, lower the radiation. Okay, like aluminum foil is very good to place outside of any object by which we avoid radiation trap inside the object. And aluminum foil is also placed in some of the buildings, like alco bond sheets. They have aluminum sheet on its upper surface which reflect all the sun radiations. So it's lower the radiation, lower the emissivity value, lower the radiations. And we have a different values, like it vary from 1 to 0. Okay. And surface area, we already have utilization have in conduction convection the same as we in the radiation. And in the conduction convection we have a temperature, we have a difference of temperature, like Ts minus T infinity, T1 minus T2. But in radiation we have a power of 4, not a power of 1. Okay, so we cannot apply the temperature in degree centigrade. You can see that in the conduction convection we solve the numerical by simple degree centigrade, and it will not affect the answer, because 273 plus this will nullify the difference. But when we apply the power 4, it will not nullify the effect. So we always in this radiation formula we have to place the temperature in Kelvin unit. Okay, so when a surface of emissivity surface area has an absolute temperature T is completely enclosed by the much larger or block surface at the absolute temperature T surrounding, separated by a gas such as that doesn't intervene with radiation, the net rate of radiation heat transfer between these two surfaces is given by this formula. The important thing about the radiation you can also experience in your own life. If you go any steel mills, any furnace, when the gate of the furnace is open, you feel very heating effect. Even if you are very far away for the furnace, like 2 meter or 3 meter, so when the gate of the furnace is opened, there is not enough time that heat air will come to touch your body. So you immediately feel or experience the heating effect. That is due to the radiation, because the radiation transfer to the body with the speed of light. There is no medium. Air is not moving from one point to 2 points, so you immediately feel the effect. And it directly proportional to very high temperature. The temperature is lower, the radiation effect is very negligible. That's why we are not feeling radiation effect in our normal daily temperatures. But if you go to the furnace, like we have a temperature like 1200 degrees centigrade, for more than 1000 degrees centigrade, you feel the radiation effect. When the gate is opened, you immediately feel the heating effect. So you can see that there is no enough time that air comes from furnace to yourself, to your body. Anyway, and another effect you can feel of the radiation, that in common I just write or cut this point over here. It is a common experience to feel chilly in winter and warm in the summer in our homes, even when the thermostat setting is kept constant. This is due to the cold radiation effect resulting from radiation heat exchange between our bodies and the surrounding surface of the wall and the ceiling. So what does it mean that assume that if you are in a room, in your own room, and you set the temperature of the room like 23 degrees centigrade. For an example, in a winter, even you kept the temperature of 23 degrees centigrade, you still feel chilly, because the radiation, which is because your body is radiating the radiation to the walls and the surrounding of the rooms. Like for this example, like first read out this numerical, then you get the better idea. Consider a person is standing in a room maintained at 22 degrees centigrade at all times. The inner surface of the walls and floor ceiling of the house, where is going, observed to be an average temperature of 10 degrees centigrade, and winter in 25. In winter is 10 degree centigrade, and summer 25 degrees centigrade. Determine the rate of radiation heat transfer between this person and the surrounding surface if exposed to surface area of 1.4 meter square and 30 degrees respectively, and the emissivity of person is 0.95 as per table 1.9, as per we already see the emissivity table. So whether it is in the winter or in the summer, the room temperature is kept constant 22 degrees centigrade. Okay, but in winter you feel chilly, and in the summer, in the 22 degrees centigrade, you feel a comfortable effect when you come outside from the any hotter surface. And in the summer, when you enter in the air conditioned room, you feel a comfortable effect. But similarly, in the winter you don't feel a comfortable effect, and even in that temperature you feel chilly, because the temperature of walls, you are seeing this walls and the surrounding have a 10 degree centigrade, and in the winter in 25. So your body temperature is 37 and the clothes temperature is around 30, okay, as written over here. So you see that your body radiate more heat in the winters. So basically you are radiating your own heating to the walls and the surrounding, so that's why you feel a chill effect. Whereas in the summer we have a room surrounding wall temperature is 25, so less amount of heat radiation comes out of your body, so you don't feel a chilly effect in the summer, in the summers. So let's solve this numerical. Yes, first we apply the formula of Q radiation, that is emissivity Stephen Boltzmann constant area Ts4 surface temperature minus Ts surrounding winter temperature. Okay, so that is emissivity value of person is 0.95. This is Stephen Boltzmann constant, areas per person is 1.4 meter square, and you can see that the temperature the person body temperature is not 30 in practical. You can check your own temperature is around 37, but in the numerical they kept 30. I think they just taken the temperature of a clothes. Okay, so 30 plus 273 we convert in the Kelvin, and the surrounding in the winter we have the wall temperature, the surrounding wall and roof temperature is 10 degrees, so they taken 10 plus 273. So the Q radiation, the radiation from your own body to the surface of the walls and surrounding and the roof is 152 watt. Your body is radiating 152 wattage of radiations. Let's check in the winter summer. As I told that in the summer the value is around 3 times lesser than in the winters. We apply the same formula but changes the temperature of the T surrounding wall temperature from 10 to 25. We get the value of 40.9 volts. So that's why in the winter, even the temperature is your room temperature, if we kept constant as compared to the summer, you feel not a very comfortable fact. You feel a chilly effect, because your body is radiating more energy towards the surrounding the walls as compared to the summer. Okay, now let's solve another numerical. That example 1.10, consider a person is standing in a breezy room at 20 degree. Determine the total rate of the heat transfer from this person if the exposed surface area and the average outer surface temperature of the person is 1.6. In the previous numerical we have a area 1.4, now we have a 1.6 meter square and 29 degrees centigrade respectively. In the previous we have 30. So, and the convection heat transfer coefficient is 6 watt per meter Kelvin. So in this numerical we have to determine the total rate of heat transfer from the person. The person is standing over here, the parameter are given over here. So now we have to calculate both convection and radiation. the person is standing with the temperature of I've just taken the picture of previous numerical, but the parameter is 29 and 1.4. So the person is radiating heat through radiation as well as convection. The surrounding air contacted this surface of the person is radiating radiation energy as well as convection heat transfer surrounding the air. So the total energy, total heat rate will be sum of convection and radiation. So first we have calculated the convection. Yes, we calculate the convection, HA Ts minus T infinity. We have the convection coefficient value of 6, area 1.6, surface temperature of person 29, surrounding temperature 20. So we get the convection heat transfer 86.4 watt, and the radiation, for radiation we apply the same emissivity value, Stephen Boltzmann constant, area, convert the temperature into Kelvin both, and get the value of radiation. So the total radiation from the person to the surrounding will be sum of convection and the radiation, that is 168.1 watt. So I hope you understand this numerical effectively. Let's coming towards one more numerical, or we split. Let's solve this numerical. We have example 1.96 from the Sangel heat transfer book. The air at 20 degrees centigrade, the convection heat transfer coefficient is 25 watt per meter square Kelvin. Blows over a horizontal steel plate, 40 K, the K value, thermal heat K value is 43 watt per meter Kelvin. The surface area of the plate is 0.38 meter square, the thickness 2 centimeter. The plate surface maintained at constant temperature at Ts is equal to 250 degrees centigrade, and the plate loses 300 watt from the surface by radiation. Calculate the inside plate temperature. So now in this particular numerical, you can see that we have to find out the temperature of this point. The bottom surface and the upper surface have a 250 degrees centigrade, in air is blowing from the upper surface. So it's also a question of you have to determine it this numerical by your own imagination, that the heat transfer should take place from this point to this point, because air is blowing from above surface. So the blow temperature is somewhat higher as compared to surface temperature. Like it is an example of some steel pan, the stove is lighting at the bottom and the air is touching the upper surface. Okay, so we have to apply, and this plate also radiate the conduct. The first heat take place from conduction between this plate, and from the top surface of the plate the heat transfer is going towards the surrounding by the convection as well as radiation, and the radiation value they given. Okay, let's solve this numerical. Now again let's okay, take another page. Now we basically we have Q conduction, is equal to Q convection plus, fan is not writing very well, Q radiation. Okay, the heat transfer is from this plate. We have higher temperature here. First we have a conduction, then from the top surface we have a convection plus radiation. So you can apply the formula to determine that its lower surface temperature Ka Ti, that we need to determine T1 minus 250, the outer surface temperature. Okay, and we have a thickness of 2 centimeters, so 2 we divide by 2 divided by 100. Okay, I'm just writing the value directly, but in the paper you have to write first formula and then write the values. Okay, and we have a formula of this HA. The outside temperature is 20 degrees centigrade, so 20 TS is 250, and we have TS. Okay, I just write down the formula: TS minus T infinity plus 300 watt of radiation. Okay, so K value is, first we have to write out the data, so we don't need to point out again the numerical. The K value is 43 and the H value is 25, and the area is 0.38 and the thickness is 2 centimeter. Okay, so we can write the K value 43 multiplied by area, that is 0.38. you see that I'm just writing Ka value, and Ti need to find out, minus 250 divided by 2 centimeter means 2 divided by 100 we have to write out in the, and the value of H is 25. 25 multiplied by again 0.38 multiplied by 250 minus surrounding temperature 20 degree centigrade, and for the radiation they just give the value of in the terms of watt, that is 300. Okay, so now it's become, when we have to solve out this, we get the value of 2185 plus 300 and multiply by this 43 and 38 divided by 2 divided by 100, we get the value 817, and in bracket we have to write T1 minus, how can I write, T minus 250, and we get the value 817. Now this 817 will divide by this, and we get Ti value, T1 value is like something like this: 2485 divided by this 817 plus this minus 250, there we get here 2 plus 250. now we get the value T1 is equal to 3.04 plus 253 degree centigrade. Okay, so we find out the value of inner surface or bottom surface of the plate. Okay, now we have covered conduction, convection, radiation, and after that we will solve the combined effect of numerical and some numerical like your related to your construction industry, like this wall heat radiation from the walls of the buildings, like bricks, etc. So we'll see in the next lecture. Thank you.